All right. Uh, thanks for coming out today to PDXRust. Woohoo! I'm going to talk today about a Rust project that I've been working on called Froyo. So my day job is I'm a Red Hatter and I work on storage stuff, LVM. Block devices, iSCSI, that sort of thing. And have been really excited by how the possibilities that Rust has for low-level systems programming. I've written a lot of C. I'm tired of writing C. I'd like to write more Rust. And especially because like one line of Rust, you do so much more than the equivalent line of C. So really, just in terms of productivity, I find myself being a lot more productive in Rust. This project that I've been working on kind of on the side is called Froyo. It's still storage related, and it's not really, this talk is going to talk a little bit about the project, but it's also going to be talking in terms of just like the different Rust things that it's doing and the capabilities that it's using. And even if you're not necessarily interested in Froyo specifically, then Froyo, there are a lot of examples that might be applicable to whatever code that you're writing as well. In addition, I like to think that Froyo right now is around 5,000 lines of code, and that's including white space. So one thing I've found with Rust is that there's a lot of like small examples, and then there's big examples like Serbo, but just trying to get more kind of medium-sized projects so that if you're interested in kind of seeing how different things are working and you can kind of like see them in action and how they're being used in a medium-sized project. So that's kind of another place where looking at Froyo might be interesting, even if you're not particularly interested in storage. So when we talked about getting fancy, well, there's certain storage on Linux, storage on any OS right now is already fancy enough as it is. You've got all these different RAID levels, you've got all these different file systems, you have ZFS, Btrfs, XFS, you have LVM, a lot of configuration possibilities, failover, multipath. But what Froyo tries to do is kind of get fancy under the covers with some of those things like RAID and thin provisioning, but then turn around and try to be as simple as possible and easy to use as possible for the user. So basically, the idea with Froyo is you have a bunch of different size hard disks lying around. You give them to Froyo, and then Froyo gives you a file system, and you just put stuff on it. And if one of the drives fails, you're okay. And if you run out of space, you just like give it individual drives. You don't have to worry about like making a new RAID set or extending volumes or anything like that. It should just like do all that for you and just like. The only thing should be like, if you give it data, it returns the data, and then if it's getting short on space, then it like lets you know and says, feed me more disks. So we're trying to be as simple as possible here, but being as simple as possible under the covers, of course, can be hard. So Froyo tries to do as little work as possible, basically. We're not trying to reinvent any wheels that have already been implemented. So there's already on Linux, there's already a really awesome set of capabilities called Device Mapper, which let you take a block device and then you can divide it up into smaller block devices that you can use for whatever, or you can take multiple block devices and glue them together, or you can take multiple block devices and glue them together and have them provide redundant storage like RAID. One of the more recent capabilities is thin provisioning. So you have a block device that can look like an infinitely big block device to the file system and kind of abstract the actual storage available from what the file system thinks is there and what the user has to deal with. So all these different tools we're going to kind of combine and hopefully put them together in a way that makes things easy for the user.
What does thin provisioning mean?
So have you heard of like a copy on write file systems? So it's the notion that in a traditional file system where you have like, you give it a gigabyte and the file system thinks there's a gigabyte, and like if you write it offset 0, then you're actually writing at offset 0, and then you just make it's as big as it thinks it is. So within provisioning, you tell the file system, I have 1 terabyte, but you only actually allocate the space when the file system actually writes to whatever sector. So it's kind of like virtual memory. It's virtual storage. You're not actually allocating the storage until it's actually used by the file system or by the user by writing files to the file system. So of course the downside of that, there's a lot of upsides, but of course the downside of that is that if the user thinks that they have a terabyte and they write a terabyte and they don't actually have a terabyte of storage underneath, then bad things happen. So that's, yes, something we need to worry about. And we'll talk more about that. So we're using the Linux device mapper framework. We're putting a file system on top. The most bulletproof one that I know of right now is XFS, which is good for big files and lots of files. But it could be a different file system down the road. Who knows? And we're also using DBus. Who here is familiar with DBus? A couple hands. So DBus is I don't know if it's Linux specific, but it's a Linux centric framework for inter-process communication. You can like enumerate services that are available, and you can make method calls, and different things have properties, and so different unrelated processes, different processes written in different languages can communicate with each other. It's used very heavily in terms of the Linux desktop integration, that sort of thing. All uses DBus heavily. So the great thing about DBus from our perspective is that, it's language independent. So if I'm writing my thing in Rust, then that doesn't necessarily mean that clients to Froyo or anything that wants to use the Froyo API needs to be written in Rust. They can be written in whatever. So that's really cool. And in fact, we go so far as that the Froyo command line tool doesn't like do its own thing and then there's like this API hanging off. It uses the same API, the same DBus API that we're exposing. So that's kind of a way to guarantee that the API is solid enough to be actually used by different things. Last of all, of course, it's written in Rust. It just creates a binary though, right? So we don't care. I mean, it could be whatever. So, but of course, we do care when it comes to the implementation of things. When one big problem with a RAID is that okay, so who's familiar with RAID? Okay, more hands. So a RAID is a way to protect your storage against any one drive failing by having multiple drives with redundancy built into them, whether that's actually having separate copies of the data or having some sort of parity scheme so that if you lose one drive, you're okay. But the problem with RAID, or one of the issues with RAID, is that it assumes that you're going to be using the same size of disks to create a RAID. So what Froyo does to get around that is we create multiple kind of RAID stripes, which would be hard to manage if you're a human being, but since we're a computer program, then we just have to build into handling multiple RAIDs. And we can create that redundancy layer, and then we can build on top of that redundancy layer. And so this is how we do it. We take the redundant storage that we got by building the RAID layers, and we create one of those thin provisioning pools that I was talking about earlier. And then on top of that, we create a thin pool, and then we put the actual file system that the user will be using on top of all that. So this is pretty complicated, and you wouldn't necessarily enjoy doing this as a user, but like I said, we're going to do all this so the user doesn't have to worry about it. So here's kind of how things look from the device mapping that we're doing, and this also maps very closely with the Rust structs and the Rust data types that we're going to use to manage the mapping that we're doing. So for example, at the very bottom, we have the hard disks that the user has given us to do our thing with. So hard disks are, that's going to give us, they're going to have a size, and based on that size, they're going to have some number of either 512 or 4K blocks that we can read and write to, because they're block devices. But like from in the previous picture, though, we're not necessarily going to want to use all of the storage from one block device to create one RAID. If we create multiple RAIDs, we're going to have part of the physical disk that's in one RAID and part of the physical disk in another RAID. So we have the block dev struct, which is going to keep track of the various ranges that are used for one and for the other. On top of the block dev, we have linear devs. Like I said before, these all need to be the same size when you're creating a RAID out of them, but you can have, you're going to have multiple chunks from the same size from multiple different disks that you're going to combine to create the RAID dev. So we have another data structure, the RAID dev, which kind of keeps track, takes all the linear devs and is in charge for talking to the device mapper and creating the actual RAID block device that we're going to be building the higher layers upon. So once you get above the RAID dev, you don't have to worry about any of the underlying stuff. You have like a new set of block devices, but they're just, you know that they're redundant under the covers. So if one of them fails, you know that the layers underneath are going to make sure that no actual data gets lost.
So the RAID dev, it needs to know that each thing is really on a different physical disk, right? Right. And so the linear dev had better not lie to it about where things really are.
Right.
Say, oh, I'm going to put one of my stripe here and another stripe here.
Put another stripe on the same one, and then you're in trouble. Yeah. So so Device Mapper uses major and minor numbers a lot. So that, wait, I guess that won't help. All right, I need to add. We need to check for that. So in terms of and then as you go up, you have another Rust data type that's in charge of. So you have these RAID devs, but of course you have multiple ones of them. So what the thin pool layer wants is two contiguous block devices to build its stuff on top of. So you actually have to use a linear device to kind of glue those back together because they could be spread across multiple RAID devs, and then you have those two apparently contiguous block devices, and then you can make the thin pool, and then you can make the thin device on top of that. And in terms of the Rust objects, they're all kind of like, they all need to like know about each other and kind of be able to, the RAID layer needs to find out how much disk space is available on the block devices to see if there's room for another RAID, that sort of thing. So there's a lot of linking between these different layers. And since we don't want to use bare pointers, we use a lot of ref counting to do that. We have the block dev has a list of the linear devs that are allocated out of it. So the disk knows which space is in use. So if we want to create another RAID, we can either say, yes, this is the space that's still available, or no, it's not available. Each linear dev knows which block dev it's allocated out of. The RAID dev knows how many linear devs make it up and which block devices they come from. And on and on up the stack. Don't need to go through everything here, but there's a lot of parent pointers, can't say pointers, or parent references and vectors of RC ref cell. Froyo uses that heavily, but that's okay because Froyo is single threaded. So if we're almost always going to be, if we don't have a programmatic error, we're going to be fine in terms of borrowing things either mutably or immutably. It's just we need to be able to access the same objects from a lot of different locations. And then, of course, we can build this structure of mapping devices when the user requests them, but we need to be able to rebuild this structure and get all the mappings back the way they were if the user, I don't know, decides to reboot their computer ever. So Froyo has from each of those block devices, Froyo takes a chunk of space and saves the current configuration as metadata. And the format that it does that right now is it has a little bit of a binary header, because you have, the way that disks work, you pretty much always know that if you're writing 512 bytes, that you're always going to get either the entire 512 bytes written or none of the 512 bytes written if the system crashes. But if you're talking about longer than that, you could get partial writes, and that's bad. So the system that Froyo uses is you have a small binary header that points to two different metadata areas which store the information in JSON, and then one of them gets updated and then updates the header, which you know is going to be atomic, and then the next time it's time to update it, then the other one gets updated and you update the header. So you're never overwriting your good metadata. You're always putting it in a new place and then writing the header to make sure that it's atomic. And we use JSON for the layout because, not that it's particularly space efficient, but I mean, disks are so big these days that if you take a megabyte, you take 2 megabytes, you write it out in text format, it's still a drop in the bucket. So let's use the data format that's easiest for us to parse, and that there are libraries that exist to parse.
Do you have redundancy in the metadata storage?
So it's written to all of the block devices at the head and the tail. It's got timestamps. So if you get some of the disks that come back, or some other one of the disks that come back, you should always be able to know the complete layout of everything and be able to put things back together. Or if you can't put things back together, you know what's missing, so that you can say to the user, hey.
So each one has all the layout, not just their own.
Correct. So now we come to the first awesome Rust library that Froyo makes heavy use of, which is Serity. Serity has macros that you can just say, like, you're defining a struct and you just say, derive serialize, derive deserialize, and then it does it from there. Unfortunately, remember what I was saying before about everything kind of having RC rush cells to all the other different layers? Serity has a problem with that because you get loops. You have your parent, and then your parent is pointing back there, and it just kind of goes around and around and doesn't support that. So what Froyo does is it has a second kind of set of mirror structs for each of the things that we want to save to JSON that that you can convert to that don't have those loops in them. Instead of having a parent pointer, you might keep track of the parent's UUID. And then when it comes to deserialize, then some code has to be written to kind of take those UUIDs and then match them up and then kind of relink things when you're recreating the in-memory objects. And that's what the toSave and setup functions do. And that's just, that's what we're doing right now. It was tempting to try to make Serity work without doing that, but that actually made things a lot easier to just kind of do that by hand. Another thing that's, I guess, kind of a good rule of thumb is so you have like things that are ordered and you have things that are unordered. Like the order of segments for a volume, you better get the order right, because volumes don't really like it when you take this part of the disk and you pretend that it's over here and that sort of thing. But disks themselves are not ordered. RAID volumes are not ordered. They could start out as being the first thing on the disk, but then through some manipulations, they could end up on an entirely different disk, and that segment could be the second RAID volume on the disk. So one thing that I found really helpful is to kind of think about that and to use either a dict or a struct or the JSON equivalents that makes it impossible to misuse them. So if it's ordered, then make it ordered, and if it really doesn't matter if it's ordered, then even if it looks like you could use a list, don't use a list, use a dict, and that'll kind of make sure that there is no order, and you're not tempted to assume an order. The next big area where we use a library is for our DBus support. So like I said before, DBus is well, you have your traditional Unix IPC mechanisms like name pipes, FIFOs, and that sort of things. And DBus is built on top of those, but it is actually pretty complex. You have objects. An object can have multiple interfaces, each of which has methods. It has properties that can be read-write or read-only properties. So luckily, there's a Rust library called DBusRust, which does a lot of that stuff for us. Unfortunately, because of everything that Froyo is doing, and because of the complexity of DBus, and because of the way that DBusRust uses a builder pattern in kind of an interesting way, this is like the hardest code to look at, because you're like making things, and there's like a lot of closures and cloning and that sort of stuff, just because you need to reference things in each method and they're attached. Anyway, I don't need to go into it, but the good news is that the code is written. I don't have to write it again. And the upstream author, this has really been a really positive experience working with an upstream author to kind of just like, there's this little feature that I need. You know, what if I do it this way? Well, it's not really the way I like it, but you know, let's do it this way. Sounds good, and then implementing it that way. So just a shout out to the Rust community of library authors as being awesome to work with. Other libraries we use, there's a library called clap, which is great for command line parsing. I like the command subcommand way of structuring my command line parsing, and it handles that quite well. It handles other styles too, the option style. And it uses the builder pattern too. So if you have, you kind of like build this massive thing and it's very indented, but then everything gets kind of taken care of from that point. We also use the byte order crate. When I was talking before about that little binary header that goes into the head and tail of the block device, we want that to work on little endian and big endian machines, so we can use byte order to make sure that that's done properly. This is a Unix or Linux specific tool, and we do use some Unix specific system calls, and the Nix crate is great for doing that. I know the Rust standard library tries to make sure that it's cross-platform, but sometimes you just like, I don't care about cross-platform, I want to make nod. So,
doesn't the libc crate also provide those?
It does. I think Nix kind of makes them a little easier to use.
I think Nix is using the sys. I mean, he's using the Nix is the syscall interface, and libc is the C interface, which are similar but not the same thing. Right? Things like make node don't exist in the C library.
In libc crate?
I don't think so. I don't think it's a C function, is it?
Okay, this isn't.
But
this is the wonder of libraries. I don't have to worry about that. It just works. Some other libraries that we use the CRC library. We use that to put CRCs over the JSON metadata that I was talking about before to make sure that those don't get corrupted. We use a lot of UUIDs, so the UUID crate. The term crate gets used for colorizing output a little bit, which is nice. The last one, device mapper crate, is something that I wrote to just kind of take all the ugliness around calling the device mapper ioctl, and there's strings that get put into buffers and input buffers and output buffers and flags and all that sort of stuff, and just kind of becoming your own library client. It's like you kind of hive that off, you put it over there. You know, when you're developing it, you wear that hat, and then once you're developing something higher level, then you can just like, that's a crate, and I'm just going to use it, and I can kind of forget about all the ugliness and the unsafe that's kind of inside there, and I can just do my thing. So you can be your own library user too.
I assume working with upstream is really easy.
Yeah, he took all my patches. So next I'd like to talk about a couple of the different ways that the Rust type system, how Froyo leverages that to kind of reduce bugs, improve development, that sort of thing. So the first thing is that instead of using, so I mean, as you probably can tell, a lot of Froyo is like ranges on disks and ranges on top of block devices. So, and those could be represented all as unsigned 64 as U64, but we want to be very careful that we don't make mistakes, because if you make a mistake, you get a calculation wrong, then horrible things happen. And you could be referring to things in terms of bytes, or what's more common with block devices is you refer to things in terms of sectors, which is 512 byte blocks. Or there can be sector offsets, or then when you start talking about the thin provisioning layer, it doesn't deal, it's kind of allocating things in terms of data blocks, which are usually like 4 megabytes. So all these different numbers, these different scalar values, you want to make sure you don't mix them up. And so that's why defining separate types for each of these, which you have to convert between, even though they're all U64 under the cover, seemed like a really good idea. So there's a library called new type derive, which, because you can define a new type for sectors or sector offset, but then you still want to be able to add them together, multiply them, offsets, that sort of thing. So, and those, instead of having to write all that boilerplate, new type derive kind of makes it easier to do that. Although it doesn't tell SERDI how to serialize and deserialize them. So if you look at the Froyo types.rs, we still have to implement serialize and deserialize for each of these new types, which once you figure out how to do it once, you just cut and paste. The next thing that we do is, so we have our Froyo struct, and our Froyo has a list of our block devices, it has a list of our linear devs, it has a list of our RAID devs, it has a list of all these different things. And what happened was the Froyo implementation got really, really big and really, really unmanageable, because anything that was, if you're like looking for, find me a terabyte of free space on all my block devices, then that was a method on the Froyo implementation. And even though it only is looking at the block devices, it was a method on the Froyo implementation. So just to kind of like break that up and group things logically, Froyo uses single item structs, like here we have one for the block devs, single item structs to just kind of give us an extra place that we can kind of put all those different block dev specific methods that are, it needs to be able to access all the block devs, but other than that, it's all concentrated in that one particular area. So let's just have this separate block dev, and then that lets us take all the code that was littering the Froyo implementation and kind of move it into separate implementation, just to kind of keep things straight. So
the idea is block devs is kind of a new type around just a B-tree map, but
right.
It lets you implement your own methods on it. So
right. So it's kind of just an organizational, take this out of the Uber struct and kind of put them over here, organizational thing. So I don't know if that's a pattern or an anti-pattern, but I guess we'll find out as we go along. So another thing that we did with using Rust types is they don't, when you look at the RAID devs referencing the linear devs, which reference the block devs, it's not necessarily true that the block devs are always going to be there. So if you have three disks in your Froyo dev and one of them is missing, then you can't just pretend that you're a 2-disk RAID device. You need to know that it's like 1 and 3 are there, but number 2 is missing. So so Froyo uses and this is really a perfect example of using the sum types, the enums, to when something is there, we have a block member is present type, and then it includes all the information for when it's there. If it's not present, then we still have something that's there, and we can know that it's missing, and we can set up device mapper to handle a missing device properly. That also extends up to the RAID member, where we have a member of the RAID can either be present or it can be absent, which means that we still have the configuration, but we just don't have that particular disk right now. Or it can be removed, which is we've actually forgotten about the configuration, and anytime we put in a new, we initialize a new disk and put it in, it's going to try to look and spread itself across that new disk as to reestablish redundancy. Like I said before, yeah, the container choices kind of imply the semantics of using them. So use a map for your disks because they're inherently not ordered. And I think, you kind of start out when you're doing development, it's like put everything in a vec, and that works for a while. And then I think Rust is really good as like you change that to a different data type, and then it's just like you go and fix it up, and then you're good to go, and you can have a really high level of confidence that everything is going to fit together and work the way you want it from there on out. The last thing in terms of types is Froyo result and Froyo error. I think this is also another kind of Rust pattern, is that you have all your libraries, and each library has some result type that it is returning its results as, and you make an enum type for your project that uses all these. In this case, it's Froyo result, and you write a couple methods that enable all those different library error types to convert to the different library result types to convert to your result type, and then that enables you to use try pretty seamlessly across your code base and get the kind of fit all the different heterogeneous error types into your framework. But then you can also define your own error type and include that in the enum as well, so because you want to throw your own errors too. So when it comes to building Froyo, how many people here are familiar with Clippy? Okay, majority. So Clippy is extra lint checking for your Rust code, which you're like, oh yeah, I did do that, and then you fix it, and then you feel better. But when you first turn Clippy on, you feel dirty until it's clean. The only trick about Clippy, or at least in Clippy on Nightly, is that it brings in some dependencies, and sometimes things break for a while, but eventually they get sorted out. But it can get a little rough. So for Clippy and for Serdi, which also kind of has the same problem of as Rust Nightly, as the compiler advances, things break, and then libraries get updated. So it's just like finding that snapshot of everything where all of your libraries and all their dependencies work. So multi-Rust really comes in handy for that. It's like, okay, I know Nightly 2015 5.15 worked with all my libraries, and then I do a cargo update, and that updates all my dependencies, and I update the Nightly compiler, and everything breaks. And then you kind of like do that, and then there's a day where everything works, and then you're like, all right, that's the new snapshot, and then you can kind of go. That definitely doesn't sound like a pattern, but that's what we're doing right now.
Snapshot is newer than that.
What's that?
I hope your current snapshot is newer than 2015.
Well, almost everything worked. It was just there's one library that needs to be updated, so hopefully I'll keep checking it. So there are still some unresolved issues. So Froyo is a very I/O talking to the OS kind of thing. So we're doing a lot of I/O results, things that return I/O results. We're using try a lot. We have actually more than 300 calls to try in the code, and it's been very easy to you just write try, and then you return your Froyo result, and you don't have to worry about it. But that really is not good enough. There's going to be cases where where you want to do things fail gracefully, and so we need to go through the code and really think about each of those tries and say, okay, this is this can just go through, or this one we need to actually match on and do something. We need to clean up something or do something smart. So there's a cost there. The next thing is on Linux. There's a system called UDEV, which, like, whenever you plug in a drive, you can get a UDEV notification, which is nice. So Froyo needs to integrate with that. So you can have, again, if you have like a 3-disk Froyo dev and you have 2 of the disks inserted, well, you could come up in degraded mode, but if you're waiting for that 3rd disk, then you could come up in redundant mode. And so you need to get that device notification. You could come up with just 2 disks, but then when the 3rd one comes, you want to see that it shows up and then go into redundant mode. So the UDEV, I mean, that's kind of I don't know if it's fair to call it a dark corner of Linux, but it's a corner that not that many people have to deal with, but I don't know, maybe it won't be that bad. There's still some missing features. I've been working a lot on the shrinking, so it's like you have 3 disks. You don't have that much data on your Froyo dev, but you have 3 disks, and then one of them fails. So now you're not redundant anymore. So if another one of the 2 drives fails, you're going to lose your data. But if you're not using that much space, you can like reconfigure the 2 remaining drives and reestablish redundancy on those 2 drives. So that's got that working right now. But the case where you have 3 drives and then you add another drive, so you have more capacity. So all your RAID devs should get bigger. Still working on that. The throttling is getting back to what Jim was saying about thin provisioning, where you have a certain amount of space, but the file system thinks that you actually have more space than you have. And what happens when you use more space? I mean, because it's just going to like keep going. If it thinks it has a terabyte, it's just going to, yeah, I'm just going to write this block and write this block and fill it up until enough space for itself. But there's this hidden constraint that it's now under, based upon the thin provisioning layer under it, that if it runs out, then it's going to be hating life. So the way that some thin provisioning solutions handle this is to just get, when you approach that running out of thin provisioning blocks, is to just get progressively slower and slower, so that you never actually fill up your thin provisioning blocks. Which there aren't a whole lot of other options actually, because I mean you can like lose data, or you can just get slower and slower, or something like that. So probably, at least initially, we'll try the throttling approach and see how that works. The second to last one is interesting. I was talking before about working on the shrinking case, and it's been very tricky. You've had to like overlay a mirror on top of existing stuff, but the kernel has gotten better, or is getting better in the meantime. So it's getting support for these VM RAID layers to reshape themselves. So, okay, so now I could, in some future kernel, I'll be able to take advantage of that. But that would mean that we could only have that feature on that kernel or later. So this is a case where we might want to support the reshape on those kernels, but still have the older, clunkier method, the manual method for older kernels or that sort of thing. So and I think there's trait objects might be the solution, where we can figure out what kind of kernel we're on early on, and then set up that, and then call methods on it or something like that. Haven't had to worry about that yet, because they posted the patches, but they're not in the upstream kernel yet. The last unresolved issues is distro support. So I understand that Rust stable is in Debian, which is awesome. It is not yet in the distro that I care about, which is Fedora. It's making slow progress, which is great. And I think there's been a lot of work on both the Rust side, and I wish there's been a little bit more work on the distro side to make that happen. But I think it's getting closer. I'm hoping sometime in 2016 it'll get in there. And I think that's really going to kick off, at least for me, I mean, that's going to be a big motivator to get off nightly. You know, if we have to use another JSON serialization, then I think it's worth it at that point to start getting in distros and getting into those distribution repos. So that's really it. There's a link to the GitHub repo. Like I said, you don't necessarily need to be a storage geek to just kind of get a sense of the different Rust paradigms that are in use for what we're trying to do. We have a very sparsely populated IRC channel and very sparsely populated development list, which is big until you make it. So, any questions?
How do you test things, especially those drive failures, to make sure that the code you've written actually works as expected?
You can use virtual machine. Oh, yes. So the question was, how do you test for drive failures and make sure that things are working as expected? You can use virtual machines for a lot of that, like surprise removal. You know, the disk goes away. And also you can use Device Mapper. Device Mapper has some targets that will lay over an existing target and return error codes. And then if they're under the RAID layer, then the RAID layer will handle those and freak out when it starts throwing errors. So haven't actually got to that stage. I'm still more in the handling device removal at this point. But virtual machines are awesome.
How does the serialization deal with changes in your own structs?
How
that's
does
a broad question that I don't know how Rust handles it, but if you add or remove something from your struct, what happens serially to deal with that? Because you're writing these things to disk.
Right. How does serialization handle changes in your own structs? Well, I think that we have, I mean, once you write something to disk, you're committing to a format. So you can either, if you decide to change that format, it becomes a much bigger decision at that point. And you can either start over with Froyo 2, or you can have some sort of conversion mechanism, or you can just change your code so that it handles both. I know a lot of existing file systems have done that. Or, I mean, LVM has been around for a long time. It actually also has a text-based metadata format, but it's managed to evolve without a whole lot of changes this whole time. And I think actually being text-based helps with that.
So I wonder that one partly as a library author, that people wanted to add seri support into the big int stuff, for instance. And I went ahead and committed that, but I don't know if that now means that I can't change big int because other people are going to be relying on the serialization looking a particular way.
Well, so you were saying something about how if you add serialization support, then that kind of commits you to a format or something.
That's what I worry about.
Right.
You can always bump the major Simber version, but it's not really a great answer.
Right.
Bump Simber, yeah.
So no, I mean, basically it means that all your internal fields are part of the interface.
Yellow shirt.
Why Froyo?
Why Froyo? So are any of you there's a product called a Drobo, which is an actual hardware device that has 4 device bays in it, and it kind of operates in the same manner where you plug in disks and it gives you a file system. So this is like that, and I think there's advantages that the hardware has in that, like the running out of disk space thing, it actually has lights on it that can like light up and you freak out when you see the red light blinking. So, but there are also a lot of advantages for a software-based approach. And I actually have a Drobo, and so it's lasted 6 years and it's still using a 6-year-old processor, whereas if you do it on the host, you have a much faster processor, you have much faster disk interconnect, and you can kind of scale with that system instead of buying hardware. So it was that's kind of where the genesis of it came from, and so yep. Yes.
You mentioned that you were using RC ref cell for switching out the folders.
Yeah.
Then since it's ref cell, that means that you make a method call to borrow it shared, or a method call to borrow it mutable. So it's dynamically tracking that the contents are borrowed. You also mentioned that you got parent pointers. So there are things where you have something pointing down to something, but then those things are also pointing back up.
Right.
Okay, so you have a cycle in your data structure, and reference counting doesn't collect cycles. Is that something that you cope with manually?
So the question was, we have a data structure where there are cycles in RC ref cells pointing parent pointers and then other things pointing upwards. How do I deal with that? So I don't think that bites Froyo as much, because each of those is also representing a device mapper target, which are built on top of each other. And when it comes to tearing them down, you kind of build them up and then you tear them down. And so I think that the thing that would have a parent pointer would go away, and that would decrease the count. And then when these things go away, then there still is a reference to that until the parent device gets removed, in which those counts get decremented, and then it would be cleaned up. So
Parent device won't get removed as long as there's pointers back up to it.
Right.
Unless you explicitly clear.
So it hasn't been a problem yet. We'll see how it goes.
I think you probably want to use the parent pointers to be weak. There's like RC also has a sister type called weak,
Right.
which
Also use weak pointers, but you're never going to have a parent pointer that points to something that isn't valid.
yes, you don't have memory on safety, but you do probably have leaks.
Unless you are going through your vectors and explicitly removing each thing from the vector, right? Then in your drop method, you're probably getting.
Isn't that going to happen when the structure itself gets dropped? That the elements in the vector are going to get dropped?
But that structure won't be dropped if somebody else is holding an RC to it.
Yeah, its children are pointing to it, so that thing never gets dropped.
Right, but at that point, the children have already been. Okay, I need to think more about this.
Decided that leaking is safe in Rust. So you just run out of memory.
That's not quite what they say.
Any other questions? Well, thank you very much, Andy.
Thank you.